Welcome back. When we first started talking about sampling, I introduced this picture right here that shows our original analog signal, the sampled signal, and also a quantized signal. When we combine the quantization and the sampling, we finally have our digital signal. So we've talked about sampling. We're now going to spend a little bit of time talking about quantization. So in quantization, we take signal levels and we restrict them to be specific levels. We can represent our sampling as a figure that looks like stair steps. So the idea behind these stair steps is your input signal is on the x-axis and your output signal then is represented by this function on the y-axis. So this would be x of n coming in, and this would be x of n quantized coming out. So if I were to pick a particular level at the input, say maybe here, that means the output is going to be there. And in fact, every input I pick in there is going to give me the same output. But once I cross over to the line and do any of those, the output will be there. So I can have a continuous input. The output is going to be just at specific levels. Another characteristic of quantization is that there will be a maximum value that we can represent under almost any circumstance. And at that point, we say that our system is in saturation. So in this system, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 levels. It might have made more sense. In fact, just for points of discussion, I'll restrict it to 8 levels. 1, 2, 3, 4, 5, 6, 7, 8. And this would be 3-bit. So using 3 bits, I can represent those particular levels. And this isn't quite right. If I used signed arithmetic, it would actually be just one more change. This would be 0, 0, 1, 0, 1, 0, and the last one would be 0, 1, 1. Of course, that's 0, 0, 0, and this would be negative, and so we'd do our 2's complement here. And there we go with our various quantization levels. So this is an example of signed 8-bit quantization. And typically, for audio, for example, we use 16-bit. When we're doing audio mastering, probably 18 to 24-bit would be more common. And when CDs were more common, it would usually tell you right on the label someplace, 20-bit mastering, 24-bit mastering, or something like that, to tell us that all the original processing was done with the audio represented with 24 bits, which would be approximately 16 million quantization levels. That's pretty high accuracy, and so you got a very good signal to noise ratio. But we're going to talk about the signal to noise ratio also in just a minute. But first we need to introduce a few other things. First is the space between quantization levels is just labeled with a capital delta. Okay. And notice that I have centered our quantization levels around 0. There's one other way of doing this, and sometimes this is a little bit easier. Easier doesn't usually mean better. You might see quantization levels that look like this. And generally that's not good. And the reason why is because a value, an input value right here, is going to be mapped to 0, which means for this situation, the maximum error, the quantization error you're going to get is delta. Whereas with this one, if we were to draw a line right through the middle to illustrate our perfect situation, the maximum we're going to be off is only delta over 2 for our maximum error. Okay, so with this situation, we have that our error is going to be between delta over 2, negative delta over 2, and I guess I should put square brackets, delta over 2. Okay, so we've defined the basic concepts. Let's go ahead and start figuring out how to analyze what's going on here. If we have x of n into a quantizer, which is often just specified with a capital Q, we get out our xq of n. And I'm going to change notation at this point to be x hat of n. Okay, then we can define our error. En is equal to xn, oops, minus x hat of n. And that's the error that we saw up above there. So just a few more things. It's common to, because of the way computers are built, to have 2 to the b quantization levels, where b is the number of bits we have available to us. So alright, so let's see what E is like. I'll give you some hints. One of the reasons we studied statistical signal representations and information is because we need tools like that to analyze things like E. So, what is e to the n like? It turns out that if we had few quantization levels like we do right above there, and we had an input that was, say, a sine wave, and it goes into a quantizer, and what we get out is going to be and so on. The error is going to look something like this. Where the difference between that is delta. So basically the error looks like all the chopped off parts of the signal, like you might expect. So, however, it's very clear that the error itself is going to be very much a function of the signal that we put as an input. This is going to be hard to give us some idea of what the general error is like. Is the error going to be vastly different if we, say, quantize classical music as opposed to hip-hop, as opposed to this song, that song, the beginning of the song, the end of the song? Are drums going to be quantized differently? Having signal dependence is really a problem. So, being true engineers, the first thing we're going to do is metaphorically stick our head in the sand, and we're going to approximate En as white noise. And if that's not enough, we're going to assume that it is uncorrelated with x of n. And actually, we're going to often go further and just assume that it's just plain independent of x of n. So how can it be independent of x of n if it's a function of x of n? And how can it be white when it has such beautiful structures we can see there in my example on the right? So in general, this is crazy. But it's so appealing that it's worth it to try to figure out when this will work. And so, with a few rules, it can work. And it turns out these rules aren't that onerous. The first one is that x of n should cross multiple quantization levels between samples. So it's clear that that rule was not kept in this little example I have up here with the sine wave going into the quantizer. In this case, although I didn't draw the samples, it's kind of implied that we have many samples that are all adjacent to each other, and we go and go and go until we finally hit a quantization level. As a result, everything is the error samples are effectively adjacent to each other, highly correlated with each other. But if we were to have so many quantization levels, or the signal's large enough or moving fast enough relative to these quantization levels that it's going to land several quantization levels away, it'll be hard to predict exactly where it's going to land in that point. In other words, that effectively spreads out our error samples so that when the quantization occurs, they don't show very much correlation. Okay, to do this, then we need to have the quantization points sufficiently close, and B, the signals should be varying quickly. And 2, we can have no saturation or overflow. So saturation occurs when the input signal is so large that we max out our representation. So at some point from this point on, and from this point on, we have saturation occurs. When saturation occurs, that means that En is greater than delta over 2. So we don't want that. So as long as these two rules hold, then our error is going to be uniformly distributed between minus delta over 2 and delta over 2. It will be white. Okay, now we're back into familiar statistical territory, and we can explore, characterize this noise and see how it's going to affect our signal processing operations.